Hello everyone! And finally, we are doing a intro, at least, to complex analysis. What this tutorial, or sort of 101 guide, seeks to do is basically go from sort of the basics of complex numbers. So I'm going to kind of assume you're familiar with them already in the complex plane, and what we're going to do is essentially build up from the basics, go into line integrals, and then go into the residue theorem. This isn't going to be in extreme mathematical detail at all whatsoever. For that, I will probably leave a textbook down in the description. But this is just sort of like you wanted to learn contour integration, let's go do it, without being too bogged down with technicalities and such, although they are necessary, I should add. Anyway, but the first thing we're going to do is just kind of look at complex numbers. And for that, I'm just going to draw our complex plane right here, with our reals on this axis right here, and our imaginaries on this axis right here. And as you might be familiar with, if say I wanted to plot some points, like say 1 plus I right here. Say we'll call this z1. Well, how would we plot that point? Well, we would go, 1 in the real direction, because that's 1, and then 1 in the imaginary direction, because you have a 1 in front of that I. So our point is just going to be, that right there. Say we wanted to plot, I don't know, one other, just so we kind of see where we're going with this. Say we call z2 is equal to 2 minus I right here. We're going to go forward 2, and then because there's a negative in front of the I, we're going to go down 1. So that right there is z1, and that right there is z2. So this is sort of how we plot points in the complex plane, but there's actually a second way we can express points like this, and that's with Euler's identity. So you may know, this is used in a lot of very clickbaity YouTube videos. You may know that, say, e to the pi I, like plus 1 is equal to 0. This is like, quite famous. But the more general version of that is e to the theta I, where theta is any number really, is equal to cosine of theta, and then plus I sine of theta. So if we kind of compare the two, we can plug in pi, right? And what we find is, we have cosine of pi plus I times the sine of pi. And we know that the sine of pi is 0, so there's no imaginary bit here. But we know that the cosine of pi is negative 1. So we find that e to the pi I is negative 1, or if you add 1 to both sides, you get that famous result right there. But the main reason I'm bringing this up isn't to, be like, oh yeah, that's cool. It's actually so we can express points in the complex plane like this. So what I'm going to do is consider, you might have to trust me a little bit here, but just consider this. Some r, where r is just a real number, times e to the theta I right here. This right here, if we expand it out into real and imaginary parts, is r cosine theta plus I r sine theta. And this might look awfully familiar, or similar to the parameterization for a circle. And that's because it really is essentially, if you hold r constant and let theta vary, what you're going to get is a circle in the complex plane of radius r. So that's one way to think about e to the I theta just by itself. And then you add in the r, you can, increase and decrease the radius of that circle. But this is, in a way, a form of polar coordinates, because we have our r right here, our radius, and then we have our theta right here, how much we're deflected from our x, or our real axis, positive real axis, in this case. So say we want to express z1 in terms of r times e to the theta I. What we're going to do then, I'll scooch this on over here. What we're going to do is we need to find the radius, how far away 1 plus I is from the origin. And the way we're going to do that is find z1, and then times z1 star, or sometimes it's denoted with a little bar on top. The point is that it's Z1 conjugate. In quantum mechanics, it's usually like a star, but sometimes they use the bar. In complex analysis, in the textbook I have at least, it's used as a bar. It doesn't matter too much. It can also just be denoted as like Z1 squared. There's lots of notations for this, but the point is that we're going to be multiplying 1 plus I, and then times 1 minus I. And foiling this out, we find this is just, well, 1 and then minus I squared. And then, well, it's like a, you'll notice that the other terms cancel, so I'm not going to write those out. But I squared is just negative 1, so this is equal to 2. But this is isn't our distance, this is our distance squared, right? So what we're going to do is, well, just take the square root of it. So our actual distance from the origin is equal to the square root of 2. And that's basically how we find r. And this is the square root of 2. And now we just need to find e to the theta I. Or, sorry, really just theta here. And you might be able to do this one at least kind of heuristically. You might just look at this and say, oh, well, right here, our coordinates are, well, it's like 1, 1, essentially, in the complex plane. And from, say, the unit circle, or just kind of guessing, you say, oh, well, that's a 45-degree angle. And that is correct, but our theta in this case is actually going to be in radians. So it's going to be pi over 4. But say we wanted to be a little bit more not heuristic about it and be a bit more sure on where that comes from. What we can do then is say our theta is going to be equal to the inverse tangent of 1 over 1, which is going to be equal to, as before, just pi over 4. And in general, it is going to be your imaginary bit over the real bit, just because of the way the complex plane is set up. So this right here is then the square root of 2 times e to the pi over 4i. And there we have it. One other very important coordinate to know, actually, is just that I right here. I'll kind of write this on the bottom. I is equal to, at least in principle, pi I over 2. We will be using that later on. That's why I'm bringing it up here. So now that we've covered Euler's identity and kind of basics in the complex plane, let's go on to some line integrals. So that kind of also brings up the question, what is a line integral? I'm going to assume you're familiar with them, but just to sort of recap. So say we have an x, we have our xy plane right here, kind of taking a step back. Normally in calculus, say I have, well, in normal calculus, you have some curve here, something like that, and you choose your a and your b, and you find, the area under it. That's essentially what an integral is. But you'll notice we're integrating over the x-axis. We're saying we're letting x vary from, say, well, from a to b in general, but it could be like -1 to 1, or really anything, right? The whole idea of a line integral is saying, well, what if we didn't integrate over the x-axis? What if we sort of just, I guess, the way I like to think about it is, what if we sort of bent the x-axis and integrated over something else? So, for example, we could say, have this random curve right here, and we want to integrate the function, I don't know, f of x equals, I don't know, x over it, right? What you would do is find the parameterization for this function, and then evaluate the integral that way. And the same idea really holds in the complex plane as well. So let's do an example real quick. Scroll on down. Let's let f of z equal 1 over z. Real fast. And for this example, I want to do two line integrals. One is going to be over the circle, z equals 1. And the second one is going to be over the square with side lengths of 2. So where this is 1, that's -1, this is negative I, and that's positive I up here. And I'll redraw that whenever we actually get to evaluating that. But let's focus on this one right here, this circle integral, or yes, circle line integral. What we have then, to kind of visualize this, is it's literally this. We're integrating around a circle, integrating this function around a circle, counterclockwise, I might add, around the origin. And to do this, well, we know the parameterization for a circle. We basically just did it right here. We know that for a circle of radius 1, we can parameterize this as saying z is equal to e to the theta I. So our integral, which is 1 over z dz, is going to be over this contour here, or that line. So what we can do then is substitute in the z for this, but then we also have to replace the dz. So dz is just equal to I times e to the theta I. Nothing crazy there. So now we have, this is equal to our integral of 1 over e to the theta I, and then times dz, sorry I forgot the d theta, which is equal to I times e to the theta I d theta. And now you might be wondering, well, what are our bounds for this integral? And the answer to that is actually just going to be 0 to 2 pi, because we're integrating around the entirety of the circle. We're going from this point right here, which is going to be 0 radians, to this point here again, which is 2 pi radians. So we're going to go from 0 to 2 pi. Now you might be wondering, well, what if we made that 2 pi 4 pi? Because after all, we start and end at the same point. And the answer to that is that's the equivalent of going around twice. So this is going around once. If we made that 4 pi, we would end up going around the entirety of the circle twice. Which I believe does happen sometimes. Like I believe there's one contour with the beta function where you have to go around twice. It's funky, but quite cool. I need to look into that more. But I digress. But actually evaluating this integral that's been sitting here, we find that these two terms right here just cancel these e's. And what we're left with is this I right here inside the integral, which I'm going to put on the outside, I times the integral from 0 to 2 pi of d theta. But that right there is probably the easiest integral we've done so far on the channel, which is this is just 2 pi I. And now for those of you kind of familiar with complex analysis, at least a little bit, might be like, 2 pi I, that's a very familiar number, and yes it is. I'm getting there, don't worry. Okay, so let's do a slightly more complicated example, which is going to be this square right here. So this square, where the edges are 1 plus I, and then you have 1 minus I, negative 1 plus I, or sorry, minus I, pardon me, minus I, and then negative 1 plus I right here. That's where our corners are. And one thing we can do with contour integrals is actually, to evaluate them as a whole, we can split them up into parts. So what I'm going to do is I'm going to zoom in on here and call this bit right here gamma 1, this bit right here gamma 2, gamma 3, and gamma 4. You'll often see this when you do contour integration. So our entire integral right here, which we can write as this, which is essentially the same thing as this, just this notation right here denotes that it actually is a closed line integral, or implies that at least, whereas this one right here doesn't actually imply that it's closed. But essentially, for this context, it is the same because we're going around, C, so it doesn't matter too much. But this right here is going to be the integral over gamma 1 plus the integral over gamma 2 plus the integral over gamma 3 plus the integral over gamma 4. So let's actually get evaluating these integrals and see what on earth actually happens when we do. So we're going to parameterize essentially all of these. So for gamma 1, we're going to have z is going to be equal to 1 plus ti. And for gamma 2, we're going to have z is going to be equal to I plus t. And then for gamma 3, we're going to have z is going to be equal to negative 1, yeah, negative 1 plus ti. And then for gamma 4, we're going to have z is equal to negative I plus t. And the reason for this, I'm going to leave it up to you to kind of, well, not necessarily make sense of, but just kind of verify that these are actually correct, and just you can vary t along each of these and see that you do end up with each of these line segments right here. So now we're going to have to evaluate integrals with these. And this is the part where it does get a little bit messy, but it's actually not too terrible. So what we're going to do now is find the integral over gamma 1, which is going to be the integral, because we're still doing this 1 over, sorry, I should have specified, f of z is still just 1 over z, that's the function we're integrating, is going to be the integral of 1 over z, well, dz. Well, this is just going to be equal to, for the gamma 1 integral, 1 over 1 plus ti, and then times, we need to convert dz to dt, and that's just kind of an I, so I'm just got a little dot right there, and then dt, and that's going to be from just negative 1 to 1, because we're going from negative I to positive I. Okay, that's good. Gamma 2. This is going to be quite similar as well. I'm not going to write integral of 1 over z dz for every single one, because, I mean, it's rather repetitive. But what I am going to write for this one is going to be the integral from 1 to negative 1. The reason it's that is because we're going this way in our contour. We're going counterclockwise, as we usually do. There are a couple of cases in complex analysis where you don't go counterclockwise. I actually did a video where I did do that. You get the same result, more or less, I believe. But anyway, that's for later. But the integral from 1 to negative 1 of our 1 over z, but our z in this case is I plus t. And then the numerator, we're just going to have a good old 1 dt. Our integral over gamma 3 is going to be equal to the integral from 1 to 0, or 1 to negative 1, pardon me, of I over negative 1 plus ti dt. And then, let me zoom out a tiny bit and scroll down. And then our integral over gamma 4 is just going to be along similar lines, just from negative 1 to 1 of 1 over negative I plus t dt. And so what we're going to do now is add up all these integrals and then just, well, integrate. And that seems really terrible, but it's actually not. And the reason for that is I'm just going to simplify some of these at the moment. So I'm going to get them all in the form, because these are more essentially natural log integrals. I'm going to get everyone with a 1 plus and then some coefficient t. So to do that for this one, I'm going to multiply the top and bottom by I. So we're going to have I over negative 1 plus it, but then I'm going to also switch the bounds, so it's going to, the negative I'm just going to apply to the bottom, so we actually have 1 minus ti right here, dt. Yes. Okay, yes, sorry. And then for this one, I'm also just going to switch the bounds. Sorry, I just wanted to make sure I was doing this correctly. I'm going to switch the bounds and also apply the negative. So we have I over 1 minus ti dt. And then for this one right here, it's going to be essentially the same thing. So from negative 1 to 1 of, I'm going to multiply everything by positive I again. Multiply everything by positive I, we have 1, and then plus ti right here, dt. So, what do we have here then? Well, you'll notice we actually only have to evaluate two integrals, because these right here are the same, and these right here are in fact the same. So our total contour integral, I'm going to zoom in right here, and write this off to the side. our total contour integral then is just going to be equal to the integral from -1 to 1 of 1 over 1 plus ti dt. Sorry, there should be a 2 there. 2 times the integral of -1 to 1 of that. And then plus the integral, 2 times the integral from -1 to 1. Yes, I did get that right. Okay, of I over. Oh wait, hold on. I do apologize. That is no, there's an I there. Sorry. Boop. There should be an I there. Apologies. Okay, I got scared there for a second. Okay, 2 times that, and then 1 minus 1 minus ti right here dt. And these right here are really just natural log integrals. So here we have, this is going to be 2 times the natural log of 1 plus ti right here. And you can verify that, just differentiate with respect to t, and you get that extra term of I in the numerator. But for this one, it's going to be slightly different. Our only difference is because we have this negative right here, it's just going to be negative 2 times the natural log of 1 minus ti. Yes, that is correct. Okay. And then all we have to do is evaluate this from -1 to 1. And to do that, we're just going to, well, essentially just plug and chug, as they say. So here we have 2 times the natural log of 1 plus 1. Sorry, 1 plus I minus the natural log of 1 minus I. And then here we're going to have, minus 2 times the natural log of 1 minus I. And then plus, or sorry, that should also be a minus. It becomes a plus with the negative on the outside. But minus the natural log of 1 plus I. When do you get one more parenthesis in there? Yeah, okay. And what you'll notice right here is that we only have 2 terms to evaluate. Again, we have this natural log of 1 plus I and this natural log of 1 minus I. In grouping our terms together, we actually find that we have 4, this is equal to 4 natural log of 1 plus I minus 4 natural log of 1 minus I. And evaluating this, again, really is not too terrible. Because if we actually go back to what we did at the beginning of this sort of tutorial, we find that we can express, say, 1 plus I as some real number times e to the something. And in this case, this e to the something is just this right here. So, going back down, we can express this 1 plus I actually as the square root of 2 times e to the pi I over 4. And similarly, I will leave this as an exercise to the reader. This is going to be the square root of 2 e to the minus pi I over 4. We're just going to be using the principal values right here. So yes. So doing that, we find that, I'm going to factor out the 4 just for now. We find that this is, by properties of logs, the natural log of the square root of 2 plus the natural log of e to the pi over 4, but, natural log and e are inverse functions, so we're just left with pi I over 4. And then we're going to have minus the natural log of that right there, which is still going to be, again, splitting this up by properties of logs, so this natural log of the square root of 2, but then minus the natural log of e to the minus pi over 4, but the minuses are going to cancel, and we get pi I over 4. And these right here cancel again, so what we're left with is 4 times all of this, which is just pi I plus pi I, which is equal to 2 pi I. And this is the point where you might be extremely skeptical, asking why on earth, if we integrate around a square, is it the same thing as if we integrate around a circle? They're both pi I. And the reason for that is really like the central part of complex analysis, namely that if a function it has a simply connected domain, never mind. That's theorem 13. But basically, in the complex plane, say I have some function right here, and I'm integrating it over some contour, right? And it has a pole, as 1 minus x does, at like 0. Basically, if I draw any like connected shape, simply connected shape around here, the value of that is going to be the same no matter what shape I draw, so long as it is, again, simply connected. So both of these contours have the same value for 1 over x because they both contain this one pole right there in the center. And this is, of course, assuming that they both are analytic functions and that right there, the path is a simply connected domain. Basically, mean an analytic function is essentially one that can be expressed as like a power series locally. But that's a little bit outside of what I want to get into in this video. But what I want to do now is that the fact that both of these are pi I implies that something deeper is really going on. And that deeper thing, namely, is the residue theorem, or specifically Cauchy's residue theorem. And that right there is this. It's that the integral over some contour, say gamma, of some function of z dz is just equal to 2 pi I times the sum of all the residues. This should really be like, we're summing over all the residues, like zj right there. That right there is the residue theorem. Now you might be thinking, what on earth is a residue? Well, the residue is actually just a minus 1. It's going to be the coefficient of the, I guess what you might call the negative first term in the Laurent series. So we can express f of x, or sorry, f of z, as say, a series of something as a power series essentially, but around this point right here, zj, we can express it as basically a negative 1 over z, and we're going to have other terms as well. But it's this term right here that gets our attention and is in what is called the residue. And that might not make the most sense. So here's a nice formula for the residue. The residue of some function of z at z naught is actually going to be equal to, this right here is just equal to 1 over m minus 1, where I'll explain what m is in a second, times the m minus 1th derivative with respect to z of z minus z naught to the m times f of z. Yes, I did get all my parentheses. Actually, I'm sorry. There should be this should be a limit actually. This is the limit as z approaches z naught. Sorry. And that right there is the residue theorem. And what m is essentially the degree of the pole that we have. So, for example, let's take our f of z is equal to r1 over z. The degree of that pole is just going to be 1, and that's because we can multiply this function by, say, another z, and what we're going to get is, well, we're going to essentially eliminate that pole right there and just end up with a 1. If that were 1 over z squared, the degree of our pole would be 2, and m would be 2, and so on and so forth. So let's now do our original example right here with this, our two contours right here. Let's do that, but now let's do it with the residue theorem. So what we have then is f of z, I'll write one more time, f of z, or actually no, I should really do that down there where you can see the formula. Okay. What we have then is this right here, and our contour, I'm going to tell you, is, or this function is analytic, this is a simply connected domain, and, or at least around that pole. And essentially the residue theorem does apply in this case. So we're going to be integrating, this should be note that we are integrating counterclockwise whenever this residue theorem is used. or sorry, this one right here. If it is you're going counterclockwise, you would add, or sorry, clockwise. If you're adding if you're going clockwise, you'd add a negative right there. But anyways, let's do this example now with, let's do this example now with the problem we just did. So f of z is 1 over z. So we now know by the residue theorem that the integral over gamma is just going to be equal to 2 pi I times the sum of the residues. So the residue at wherever our poles are. I should have stated that earlier, but zj is just wherever our poles are, wherever the function essentially has some sort of like asymptote. Essentially, that's one way to think about it. That is poor language on my part, but just as to begin to conceptually understand it, that's what it is. 2 pi I times the residue at 0, because that's the only place where, well, that function is like undefined, you could say. So we have 2 pi I times the residue at 0. So let's now find the residue at 0. And this looks really terrible, this formula right here. But it really isn't once we start plugging things in. So the degree of our pole is 1. So m minus 1 is just equal to 0, meaning that we have the limit, or actually I'll write this here. This is equal to, 2 pi I, but then times the limit as z approaches 0 of 1 over, 0 factorial, times the 0th derivative, so we aren't differentiating anything actually, of z minus z naught, but z naught is just 0 because that's where our pole is. We have, z to the m, but m is just 1, times f of z, which is just 1 over z. And this right here is actually quite easy to evaluate because the z's here cancel. 0 factorial is just 1. So it's the limit as z approaches 0 of 1, but I mean, that's just going to be 1 because if we have a constant function, so that's it, as we approach 0 from any direction actually. What we have right here is just, it's still going to be 1. So this right here is just going to be equal to 2 pi I and then times 1. So it's just 2 pi I. So that right there is sort of the basics of complex analysis. It's like an introduction to the residue theorem. So let's actually do one more. Let's do one more integral right here. One more example, and I think that'll be helpful. So one thing you can also do with complex analysis using this residue theorem is indefinite integrals. So integrals from, say, negative infinity to infinity. We have 1 over x squared plus 1. Or sorry, I'll make these z just to be consistent. So the integral from negative infinity to infinity of 1 over z squared plus 1 dz. Now we can evaluate this rather easily just using normal calculus techniques. We say this is, the derivative of inverse tangent, and then we just evaluate the limits of inverse tangent. But let's do this a slightly more interesting method, namely using the methods we just learned. So let's do that. Now you might be wondering, well, if we want to use the methods we just learned, well, what contour should we use? And the answer to that is there are a couple of just quite common contours that you use in complex analysis. One is, let me actually draw. Let me draw axes for our graphs actually, just for a couple examples here. One of the contours used is just the semicircular contour, where you're integrating over the entire real axis, at least in the limit, going counterclockwise, of course, and then you have a semicircular hump, essentially, on top. Another very common one is actually a keyhole contour, so you're integrating around the origin, and then you're integrating over the positive real axis 2 times, essentially, but in different directions, and then you're integrating over an entire circle. This big circle goes out to infinity, whereas this circle at the origin closes in on it. And we're integrating this way over that, and that way over that. So these are two quite common contours you really kind of see in complex analysis. You'll see others at times, like another example is like a dog bone contour right here. Um, and also other methods is involving trig functions, but that's usually just you're integrating around the circle in the origin. So this might beg the question, well, which one do we choose for this right here? And the answer is going to be this one right here. And that is because, well, you look at our bounds. They're from negative infinity to infinity, and we want to be integrating over the entirety of the real axis. So to do that, let's integrate over that contour and see what it tells us. So, well, I should probably put the whole integral on the screen. Actually, I'm going to scroll down and just rewrite it. So we're going to say our f of z now is just going to be our integrand. It's just going to be 1 over z squared plus 1. There are actually some cases where to evaluate integrals you don't want your f of z to be just your integrand while you're integrating. You'd prefer it to be something slightly different, but I'll probably cover that in a different video. So say this right here. We have the integral from negative infinity to infinity of f of z dz. And what I like to do when doing integrals like this is find our poles just straight off the bat. So where are the poles here? That's just going to be when the denominator is equal to 0. So when is z squared plus 1 equal to 0? Well, should be rather clear. This is just going to be z equals plus or minus I. But there is a very important thing right here. We don't necessarily care about the negative root right here. We don't really care about the negative I. And the reason for that is because whenever we integrate over, say this right here, whenever we integrate over that, only one of our residues is actually included inside the contour, and that's I. The other one's just kind of sitting down here. That's not included in the residue. And if you think back to our residue theorem, it's the sum of the residues inside of gamma. So because of that, we really only are concerned with the z equals I, with that pole right there. So let's now go ahead and evaluate this. We find then that the closed line integral of f of z is, let's actually start with the residues, then we can go on to evaluating the integral. So we have 2 pi I times the sum of our residues, but we only have one residue. So it's just going to be the residue at I. And now thinking back to our residue theorem, we have the limit as z approaches I of 1 over, well, the degree of the pole is still 1, so it's still 1 over 0 factorial, times, well, the derivative also goes away because the degree of our pole is 1. It's what we call a simple pole. Times x minus I, sorry, z minus I, pardon me. z minus I times 1 over z squared plus 1. I cannot write today, or at least at this moment. Z squared plus 1. So this is our residue right here. But one thing we can do with z squared plus 1 is just factor it. So we can say z squared plus 1 is equal to z plus I, and then times z minus I. And this right here is actually going, when we factor it like this, one of the terms is going to cancel with the z minus I up there. And what that leaves us with is that this whole residue right here is equal to the limit as z approaches I of 1 over 0 factorial times 1 over z plus I. But 0 factorial is just 1, and plugging in z equals I in this to evaluate the limit, we find that this is just 1 over 2I. So because this right here, our residue is just equal to 1 over 2I, we end up getting 2 pi I times 1 over 2I, which is just pi. And now, the interesting thing about this is that we went through, we had a whole bunch of imaginary numbers, but end result was a real number. And or sometimes the tricky part of doing some of these integrals is that whenever you make a mistake, usually, or sometimes at least, your end result, when you know is real, will actually be complex. So that's kind of like a red flag, something's up. But then the second part of actually evaluating this integral is going to be actually evaluating the line integral right there. So let's go ahead and do that. We have two parts here. We have our part that is the real axis right here, and we have our part right there, which is our semicircular thing that goes out to infinity. So let's go ahead and do that. We have the integral over gamma 1, which is going to be equal to the integral from negative infinity to infinity of 1 over z squared plus 1 dz. And this is one of the reasons we actually picked this contour. That is just our integral right there, what people will also often call just I. That is our integral, just by definition, the integral over the entire real axis of that function. Now let's go on to the second one, this integral over gamma 2. This is going to be equal to the integral over, well, actually let me write the substitution real quick. So what we have is this z is going to be equal to, say, r, the radius, we're going to be taking the limit as that goes to infinity, of e to the theta I. And this means that our integral is going to be the integral from 0 to pi, because this is a semicircle, remember, of, well, we need to differentiate it, so dz is going to be equal to ri times e to the theta I d theta, and then over r squared e to the 2 theta I plus 1. This right here is often the tricky part, but whenever we think about this as, say, a limit, so the limit as r goes to infinity, it doesn't actually, it isn't actually too terrible. Sometimes it is a little bit difficult, but in this case it shouldn't be, because one way we can think about this, specifically the denominator, is as the sum of some real number plus a complex number. And what we can do essentially is say, as r gets very big and big, this plus 1 we can sort of absorb, quote unquote, into that very massive real part. The point is that it's not going to make much of a difference. So in the limit, this is essentially going to be the same as the limit as r goes to infinity, as if we kind of ignored the plus 1 term. If you've done like some sort of pre-calculus or calculus, you might be familiar with this idea where you sort of like ignore, or you only really care about the highest order coefficients in there. So we can express this then as ri e to the theta I over r squared e to the 2 theta I d theta, and I guess from 0 to pi. And the point is here is that, well, as r goes to infinity, sure, we have some complex numbers here, but this r right here is always going to be, larger than this r right here. And we know that the limit as 1 over r, or just 1 over any variable, goes to infinity, is just going to be 0. So this right here is just going to be 0. So this means that our whole contour integral, or whole line integral, pardon me, our whole line integral is going to be equal to our original integral plus our other bit, but that's just 0, which is equal to 2 pi I times the sum of our residues, which is just pi. So we conclude that I is equal to pi. Does this make sense? Well, we can we can check this quite easily for this integral right here. We can say integral from 0 to infinity, or negative infinity to infinity, of 1 over, say, x squared plus 1 dx. I'm using x's because we're not going to do any complex stuff with this. This right here is just equal to inverse tangent of x evaluated from negative infinity to infinity, which is just pi over 2 minus negative pi over 2, which is equal to pi. Boom! we did it. We did this integral using complex analysis. Now, before the end of this, I would like to do one more integral, and that right there is, namely, this right here. This is one of my favorites, or at least favorite for like introduction pieces. The integral from negative infinity to infinity of cosine of z over z squared plus 1 dz. Now, this is certainly this is certainly an interesting one, but what we have is actually a really cool result, and there are tons of videos on YouTube about this, so I thought I should kind of jump on the bandwagon at some point. This right here is again really awesome, but we're going to be using the same contour as before, and we're actually going to have the same poles. So I can draw out this contour real quick. We're going to have integrating this way. We're still going to have our one pole that we care about at z equals I. That's going to be the place where we're finding our residue. But we need to inspect this a little closer before we actually start evaluating this, because what exactly is cosine? Because cosine of I, well, that gets a bit iffy. So one thing that we can do is actually not make f of z just our integrand necessarily. We can define it as something else. So let's define f of z to be e to the z, oh goodness, e to the zi over z squared plus 1. And you'll notice a couple of things about this. Namely, whenever you take the real and imaginary parts of it, the real part of f is going to be equal to our integrand right here. It's going to be equal to that cosine of z over z squared plus 1. This is one of the reasons I also brought up Euler's identity, is because it's used a lot in integration like this. You have cosine of z over z squared plus 1. And then if you also take the imaginary part, it isn't as important because it's not our integral, but the imaginary part is just going to be sine of z over z squared plus 1. So one thing that we can do then is say express the integral of f of z, right? So let's express it as an integral from negative infinity to infinity of, say, e to the e to the zi over z squared plus 1 dz. Well, that's just going to be equal to, if I scoot this on over, that is just going to be equal to the integral, if we split the z term up, the integral of cosine of z over z squared plus 1 dz plus I times the integral of negative infinity to infinity of sine of z over z squared plus 1 dz. Now, a couple of things about this. This means that if we take the real part, of this right here, so this integral right here, we take the real part of it. Let me just finish writing this. If we take the real part of that, that just means we're left with the integral that we want originally. And additionally, if you take the imaginary part, we're going to be left with that bit right there. Though you might note that this is kind of like a special case right here, to where the integral, like this right here, this actually is just going to be equal to 0, and that's because sine is an odd function. So the integral from negative infinity to infinity of that is just going to be 0 anyway. So really the real part of that is just going to be equal to the real part, like, is going to be equal to the entire integral. But anyways, that's that's kind of like a special case. In general, this absolutely does not hold. So we need to find the real part then of e to the zi over z squared plus 1 with respect to z. So let's go ahead and do that, with that being our f of z. So this means that we have our integral, our line integral, is going to be equal to integral over gamma 1, where I'll call that gamma 1 again, and gamma 2. plus the integral over gamma 2. Instead of going through a bunch of work to show that this right here, the integral over gamma 2, is 0, I'm going to point to something that, quite frankly, I love. It's called Jordan's Lemma. So, Jordan's Lemma. That essentially states that if you have an integral in this sort of form, where you have like an e here and a polynomial times some sort of polynomial, where this power right here is like at least 1 greater than the one in the numerator, which it is, 2 compared to 0, and this right here isn't 0, of course. Then essentially the line integral of that upper semicircular bit is just going to go to 0. So by Jordan's lemma, we have that the integral over gamma 2 is going to just approach 0. I would say end of story. There's always more to it in math, but just for the sake of brevity and being concise, that's what this is right here. So now, what we have then is our whole line integral is equal to the integral of just gamma 1, but the integral over gamma 1 is just the integral over our entire real axis, which is just going to be equal to, say, I'll call this I right here. That's I. So yeah, that's just equal to I. And by the residue theorem, we know that I is just going to be 2 pi I times some of our residues. So let's get cracking with our residues, shall we? What we have then is, again, we have a simple pole. So we have 2 pi I, and then times our residue. So it's going to be the limit as z approaches I of 1 over 0 factorial, but we know that's just 1, times the 0th derivative, so no derivative at all, of z minus I, and then times f of z, which is just e to the zi over z squared plus 1. But as before, we've just factored the denominator, so we know that this right here is just equal to 2 pi I times the limit as z approaches I of e to the zi over z plus I, which is just going to be equal to 2 pi I times, well, we can just plug in I here. So the denominator is going to be 2i, but let's take a look at the numerator. We have e to the I times I, but that's by definition negative 1, so we have e to the negative 1 in the numerator. So, and it's evaluating everything and distributing, we find that this right here is equal to pi times e to the negative 1, which is equal to pi over e. So we come up here and we realize, well, hold on. Well, 2 pi I times the sum of our residues was just our integral. So this means that I is just equal to pi over e. And, taking the real part of this seems kind of silly, but, technically we should. Pi over e. This right here is just still pi over e, and that right there is the answer to our integral. I thought this was so cool when I first found it. But anyway. But this right here is, I believe, where I'm going to end this first sort of tutorial in complex analysis. I had a lot of fun making this, so thank you all for suggesting it, and I hope everyone learned something. I'm going to try to add timestamps as well later on so y'all can find parts that actually interest you, and you can don't have to scroll through the entire video to find like one specific thing. Hopefully I'll make more of these, so maybe like a more complex analysis video where we deal with like branch cuts and natural logs, and I could even do one with, say, trig functions, for example. I think that would also be quite fun. Just let me know what you want in the comments, please.